Welcome to this first primer on functions. This will be a series of few primers, and before we get started, let me point out the prerequisites. All we need is the language of sets and the basic notions associated with them. So like things like unions and intersection, X belongs to S, what does that mean? Existential quantifier, all those things. So there is a series of primers on sets available on this channel. You can consult that. And with that, let's get started. So what is a function? Again, I don't know a very formal definition. I don't think one needs to know a very formal definition. Just like when we were discussing sets, we did not give a formal definition of a set. Similarly, we are not going to give a formal definition of a function, but the informal definition will be good enough for us. So start with two sets, A and B. Both are non-empty. A function whose name is little f from the set A to the set B is defined in a certain way, but before that, let me highlight. So a function f from A to B is an assignment of exactly one element of B to each element of A. So as we said, this is an informal definition. It will be clear what is meant by this as we go along. But pictorially, we have a set A and we have a set B. A function f from A to B, what does it do? It picks an element in A and outputs an element in B. And this is true for every element in A. So every element in A has a corresponding assignment in B given by the function f. It is possible that all the elements of A have the same assignment. That's possible. But this is basically the idea. So an example, what you can think of it as, let's say you think of A as your, let's say some surface. Let's say this is the surface of some table. And the set B is, let's say, the set of real numbers. So the picture would be more like this is some surface A. And B in that case would be real numbers. And what you may want to do is, to every point on this table, on the surface, you would want to assign the temperature, let's say. So that's an example of a function. The temperature of any given point you can think of as a function. So it's a very, very natural object. And all I can do is maybe look at more examples to convey the idea. So before we look at examples, let us maybe look at some notation. So if f is a function from A to B, then we write succinctly f, then we make a colon, we write A, we make an arrow going from A to B. So when we write this, we just simply mean that f is a function from A to B, meaning it assigns every element of A some element of B, but only one element of B. Okay. And another bit of terminology, a function is also called a map or a mapping. All right. So let us look at examples. So here again, recall this is the set of all the integers, and we are defining a function f from z to z, meaning it picks an integer and gives us an integer. And here is one example. It's just x going to x plus 1 for all x in z. So that's a function. It takes an integer and just adds 1 to it. It is outputting the next integer. All right. Another example. It is again a function from z to z. So it picks an integer and gives an integer. and we define it as fx going to x square for all x in z. So it is outputting the square of what you feed it. Okay? And many times in textbooks, when functions are first introduced, what is done is you think of f as a machine which has an input slot and an output slot. So here you're feeding x, this is our function f, and here it is outputting x square. I don't know if this helps to think this way, but anyway. So this is an example of a function. And let's see another example. Again, we have a function from z to z, and this time we will define it in this fashion. So, okay, maybe I should be consistent with the colors. So it sends x to x plus 1 if x is a non-negative integer, and it sends x to x square if x is a negative integer. So this function is defined in two parts. Depending on the nature of x, it outputs what it outputs according to this rule. So if this is all the integers, here you what the function out. So this is the origin. Let's say this is 0. So the function picks something here and outputs the next integer. But if you feed it something to the left of the origin, it gives you the square of that value. So that's the definition. And what I'm trying to convey via this example is that one is very, very free in the rule by which one may define a function. It doesn't have to be one succinct rule. It could be a complicated rule which may not be expressible in some very simple equation like you see in the first two examples. Okay. So far all these functions were from the same set to the same set, but the next one is from the set of integers to the set of rationals, and we define it as fx going to x by 2 for all integers. So this is also an example of a function. Okay. Let us see some non-examples. What does not count as a function? So the first one would be fx defined as 1 by x for all x. Now what is the problem with this? To every element of A, you should get an element of B. But when you feed 0 in place of x, what you get is a nonsensical thing in the sense that it is not a real number. So this is not a function. It is not respecting a certain input, namely the input 0. It is not outputting something in B when you feed it the input 0, and therefore this does not count as a function. Okay. Next example. This time we define it as, fx equals root x for all x in R. And this also does not count as a function because when you feed it negative values, this is not defined. I mean, at the very least, this is not a real number. You may know about complex numbers and then you might say, well, this makes sense, but this is certainly not a real number when you feed a negative value in place of x. And therefore, it does not take a real number, or rather, it does not take some real numbers to real numbers, and hence this is also not a function. Okay. Another example, z going to R in the following fashion. Fn is plus minus n for all n. Now what is the problem here? It takes an input, it is outputting real numbers, but it is not outputting a unique real number. When we defined a function, we said that it takes an input and gives you a unique output corresponding to that input. But here you are getting two outputs corresponding to one input. And hence this is not a function. Alright, lastly, again we have a function from z to R, or something that is trying to be a function from z to R, but the definition is as follows. This is also not a function. because again, if you feed 2 or minus 2 in place of n, you do not get a real number. Okay, hopefully this conveys what the idea of a function is. Let us look at more terminology that is frequently used. So whenever we are given a function f from a set A to a set B, we say A is the domain of f. Sorry, what did I do? A is the domain of f, right? Just a terminology, very useful to, verbally express things. We say B is the target of f, and alternately, target is also referred to as codomain. I hope you can read it. So those are two equivalent terminologies. I think in textbooks, the word target is not used very frequently. Authors use codomain. But then I don't like using domain and codomain because they sound very, very similar. So I use the word target and I think it's very fitting. All right. The image of a function is defined as the set of all the outputs that f generates. Right? It's a very simple concept. So perhaps I'll draw a picture. Here you have the set A, then you have the function f, you have the set B. What you are doing is you take a point in A and take the image, meaning take the value that you get when you apply f to that element of A. You do it for every element of A, and then you get all the points that you are able to produce by this fashion, and that is what this set is. So the image of S is all the possible outputs that you can generate using the function f. That's all. And it's a very fitting terminology. All right. Another piece of terminology is, so suppose f is a function from some set to a set B, then B is the target. So in other words, if f is a function whose target is a set B, then we also say that f is valued in B. So this phrase that f is valued in B is saying exactly the same thing as f has B as its target or codomain. That's all. Some terminology. And it is okay that you do not remember all these terminologies in one go. As we learn actual mathematics, then these terminologies will automatically be absorbed. Right now, we have to start somewhere. We have to throw in some words. I don't think it can be helped. Okay, so let's proceed. So this is a very important notion, the notion of preimage. So suppose we have a subset S of B. And yeah, so I should say that f is a function from A to B that is given. And the preimage of a subset S of B under the function S is defined as, the notation is this, and the definition is all those elements in A which map to S. Sorry, I was defining the preimage of S, not the preimage of B. So all the elements of A which map to S under S. Right? All the elements of A such that when you apply F to them, you get something in S. So it's a very natural definition and also a very fitting terminology. What is happening in pictorial terms is that you have some subset of the set P. What you're asking is, what are all the points in the domain of F which, when applied F2, reduce something in S? That's all. Okay. Just as a piece of exercise, verify that f inverse of the target is the domain. It's a trivial statement, but anyway. Finally, let us end with some examples where we will write down the domain, target, image, etc. So this is our first example that we saw. F is a function from z to z defined in this fashion. What is the domain of f? This dude, which is z. Right? What is the target of f? This guy. Alright. What is the image of f? Meaning, what are all the integers of this form where x is an integer? And if you think about it, every integer is of this form. And hence the image is the entire target. And now the question is, what is the preimage of all the natural numbers under this function f? So what are the things that when you add 1, 2, you get a natural number? And the answer is very simple. It is all the whole numbers. So it is precisely those integers which are non-negative. This is also written as that, another notation for the same thing. So I hope you follow all of this thing. Another example. This was our second example where the function picks some integer and outputs the square of that integer. The domain is z and the target is z. The image. Image is all the possible perfect squares that you can get. So the image is, one way to write is n squared, n in n0, but that's cheating. So, I mean, there's nothing wrong with what I wrote, but maybe more informative is the roster form in this case. So this is what the image is. And now the question is, what is the preimage of all the natural numbers? So what are the things in the domain which map to natural numbers which map to a natural number under f? So the only thing here which does not map to a positive integer is the number 0, because as soon as you feed it anything, either negative or positive, you get something positive. And hence, the preimage of n is everything in the domain except the 0 integer. Okay. Another one. So again, the domain and the target are z and z. What is the image? Yeah, I don't want to do this, but let's see. So what is the image of this? You get all the perfect squares. So this much is definitely there in the image, because if you, forget about the 0. So all the positive perfect squares are there, because if you feed a negative integer and take the square, that is as good as saying just take all the squares of all the positive integers. So all the positive perfect squares are available. And this gives us all the natural numbers, because as x varies over non-negative integers, you add 1 to it, you recover all the natural numbers. So what you are getting is natural numbers union all the positive perfect squares, and hence you're getting nothing but the natural numbers, because all the positive perfect squares are themselves natural numbers. Okay, and what is the preimage of n? Well, since the image is nothing but n, the preimage you can easily figure out is that this is the entire set of integers. Okay. Lastly, suppose you have a function f from z to q defined in this fashion. I leave as an exercise for you to figure out what are the domain, target, image, and this thing for this particular function. Easy exercise. And with that, I want to end this lecture. We will continue our discussion with functions the next time. And thank you for watching.